Welcome to our deep dive. Today we have some really fascinating excerpts, and it's going to be a challenge from this paper, Algebraization of Rigid Analytic Varieties in Formal Schemes via Perfect Complexes.
Sounds intense.
Yeah. Today we're going to explore this really, I think, interesting and kind of like deep concept of algebraization.
Yeah.
And how we can find kind of like the algebraic blueprint for objects that, sort of live in this like analytic world of geometry.
Right. Yeah, it's kind of like finding this bridge between these two seemingly different worlds, like discovering a secret code that links two different languages,
Absolutely. And the key to cracking this code, at least according to this paper, lies in something called, are you ready for this, perfect complexes.
Okay.
I know that might sound a little intimidating.
Right.
But trust me, by the end of this deep dive, you'll not only understand what they are, but also, really appreciate why they're so crucial to understanding geometry.
Yeah, and what's really, I think, exciting is how this paper uses perfect complexes to show these like deep connections between rigid analytic varieties and formal schemes.
Right.
It's like finding a hidden tunnel that connects these two like landscapes, seemingly separate landscapes.
Yeah. It's like, oh, wow, there's this like underground tunnel, and they dive right in with theorem point 2, which states that a smooth and proper rigid analytic variety, and I know that's a lot of words,
Yeah.
is algebraizable if and only if its category of perfect complexes is also smooth and proper.
Right.
So what does that even say? I mean, it's essentially saying that the algebraizability of a geometric object is reflected in the properties of its like perfect complex counterpart.
It's almost like saying if you want to understand the architectural blueprint of a building, you need to study the properties of its individual bricks and beams,
Right.
So the theorem gives us this very precise mathematical framework to link these two levels of description,
Okay. I like that. I like that analogy.
Yeah.
So let's break down this idea of algebraization like a little further. So imagine you have this beautiful, intricate sculpture.
All right.
Okay. So that's your rigid analytic variety. And it exists in this analytic world with all its, curves and textures. But like hidden beneath that surface, there might be a simpler, more fundamental blueprint that kind of describes its construction, right? This algebraic counterpart.
Right.
So algebraization is like the process of uncovering that blueprint.
It's like finding the DNA sequence, that encodes the intricate structure of a living organism. Right. It's about showing that your seemingly complex object can be generated from a simpler set of algebraic instructions.
Okay, I'm starting to get the picture. But like, where do these perfect complexes fit into all of this? I mean, the name itself sounds a little, complex.
Right. So let's kind of demystify them a bit. So think of a complex as a chain of mathematical objects, linked together by specific maps. And so it's like a recipe with multiple steps, where each step transforms the ingredients in a particular way.
Okay.
Now, a perfect complex is a special kind of complex, and it has nice finiteness properties. So these properties essentially ensure that our recipe doesn't go on forever.
Okay.
And that the ingredients at each step are well behaved in a certain sense.
Gotcha. So it's kind of like a way of organizing information about these geometric objects in a very structured and manageable way.
Exactly. And by studying the properties of these perfect complexes, for example, whether they're smooth or proper, like as the theorem mentions, we can glean insights into the underlying geometry.
Oh, okay. Okay. So it's like you're analyzing the individual steps in a recipe to kind of understand the final dish.
Right, exactly.
Okay. Now the paper, it uses this term category of perfect complexes. So can you explain like what a category even is in this context?
Sure. So a category is like a universe where our perfect complexes kind of live,
Yeah.
And it's not just about the objects themselves, but also the relationships between them. So we can think of the objects as like points in this universe and the relationships as like arrows connecting those points.
Okay.
Right. And these arrows actually represent morphisms, which are ways of transforming one perfect complex into another.
Okay, so the category kind of gives us this like bigger picture, like allowing us to see how these perfect complexes interact and kind of relate to each other.
Precisely. And the properties of this category, like smoothness and properness, kind of reflect the overall structure of the geometric objects we're studying. It's like analyzing the social network of a community to kind of understand its dynamics.
Oh, I like that. That's a good one. Okay, so we have our geometric objects, we have their corresponding perfect complexes, and then we have the category, right, where these complexes reside. Now, where do moduli stacks come into play? Because the paper mentions them quite a bit.
Right. So moduli stacks are like giant organized libraries where each book represents a different geometric object. So in this case, our books are the perfect complexes, and each stack is kind of tailored to a specific type of geometric space. So for example, the paper focuses on stacks like MB, ANMB, and PerFX, and each of these represents perfect complexes over different kinds of base spaces.
Okay, so it's like categorizing and studying a vast collection of these perfect complexes, kind of like organizing a massive library into different sections and genres, right?
Exactly. And within these stacks, certain books stand out as particularly important.
Okay.
We call these the simple objects.
Oh,
So
yeah.
think of them as like the prime numbers of perfect complexes. They can't be broken down further, and they kind of serve as the fundamental building blocks for constructing more complex objects.
Oh, so by understanding these like prime perfect complexes, we can potentially unlock the secrets of the entire library.
Precisely. And the paper provides a precise mathematical definition for these simple objects, and they use something called Tor amplitude. It's a way of measuring how twisted an object is. And this twistiness, it turns out, is directly related to its simplicity.
Hold on, can you like unpack that Tor amplitude concept a little bit more? It sounds a little, well, twisted.
Sure. So imagine you have a rope. You can twist it tightly, or you can leave it relatively untwisted. So Tor amplitude is a way of measuring like how much twist there is in a mathematical object. And in this case, it's actually a condition on certain derived functors called Tor functors. So the paper uses a specific condition on the Tor amplitude to identify those perfect complexes that are truly simple.
Okay, so it's kind of like a way of filtering out the unreally complexes, right?
Right.
And focusing on the ones that are like, well-behaved and fundamental.
Exactly. So by imposing this condition, we're essentially isolating the most essential building blocks in our library of perfect complexes. And understanding these building blocks is key to understanding the larger structures they form.
Okay, I'm starting to see how this all fits together, but we haven't really talked about analytification yet, which seems to be like a crucial part of the paper's argument. So what exactly does that involve?
Right. So analytification is like taking a blueprint, which is our algebraic object, and building a 3D model from it.
Okay.
So it's the process of giving an algebraic object an analytic structure, which then allows us to study it using tools from analysis.
Gotcha. So it's about bridging the gap between the abstract world of algebra and the more like concrete world of analysis.
Precisely. And the paper uses a specific functor, denoted by G, to actually carry out this process. A functor is like a mathematical machine that takes objects from one category and transforms them into objects in another category, preserving their essential relationships. And in this case, G takes algebraic objects and transforms them into analytic objects.
Okay, so it's like a universal translator kind of helping us decipher the secrets hidden within these different like mathematical languages, right?
Exactly. And theorem 2.39 in the paper establishes this crucial equivalence between certain algebraic and analytic objects via this functor G.
Right.
And this equivalence is really a key ingredient in connecting the algebraic properties of perfect complexes to the analytic properties of our geometric objects.
Okay, so we've got our perfect complexes, we've got our moduli stacks, we've got this analytification process.
Right.
Now, how does this all come together to prove theorem point 2, the main result of the paper?
So the proof is it's kind of like a carefully choreographed dance
Okay.
with each step building upon the previous one. So it involves embedding our rigid analytic variety X into a special space called the coarse moduli space of its simple perfect complexes.
Okay.
And this embedding it's crucial because it connects X to the algebraic world of moduli stacks.
Oh, okay. So it's like we're placing our sculpture on a pedestal that allows us to view it from all angles.
Right.
And then that reveals this like hidden algebraic structure.
Precisely. And the paper then uses something called Moisezon spaces, which are special types of rigid analytic varieties that have just enough meromorphic functions
Okay.
to bridge the gap between the analytic and the algebraic realms. And so by showing that the image of X under this embedding is a Moisezon space, the paper kind of clinches the proof of theorem point 2.
This is all incredibly fascinating, but I have to admit, it's a lot to take in. We've covered so much ground already. And we've only just scratched the surface of the paper's arguments.
Yeah, you're absolutely right. We've kind of laid the groundwork, but the real adventure lies in the details of the proof.
Right.
That's where we'll really see the brilliance of the author's work and how they weave together these seemingly disparate concepts into this really coherent and elegant, like, tapestry.
I'm definitely ready for that adventure. But for now, let's just pause here and give our listeners a chance to, digest everything we've discussed so far.
Welcome back to our deep dive into this fascinating world of algebraization. Before we take the plunge into these intricate details of the proofs,
Right.
let's revisit some of the key concepts that we discussed in part one, just to kind of refresh our memory a bit.
Absolutely. I think a quick recap will definitely help us navigate the more technical terrain ahead. So, we started by exploring this idea of algebraization.
Right.
And how we can find those algebraic blueprints,
Right.
for objects that exist in this analytic realm of geometry.
Right. And we highlighted that perfect complexes are the key to kind of unlocking those blueprints.
Exactly. But before we delve into the proof of theorem point 2, let's just revisit these perfect complexes and their role in this mathematical story.
Certainly. So remember, a perfect complex is like a chain of mathematical objects, specifically modules linked together by maps, and they have these special finiteness properties, right?
Right.
That make them well-behaved and manageable.
And these perfect complexes, right? They live within a category,
Yeah.
which provides this framework for understanding their relationships and interaction.
Precisely. It's like a map of a city where the perfect complexes are like the buildings, and then the arrows between them represent the streets connecting those buildings.
I like that.
So you can navigate through the city of perfect complexes.
And the paper, it focuses on these specific categories of perfect complexes that are organized into these moduli stacks,
Right.
which are like these giant libraries,
Yeah.
right? Where each book represents a different perfect complex.
Right. And within those stacks, certain books stand out as particularly important, and we call these the simple objects.
Right.
And these are like the prime numbers of perfect complexes. They're the fundamental building blocks from which more complex objects are constructed.
And the paper, it provides a specific criterion for identifying these simple objects. And this uses this concept of Autor amplitude, right?
Yes. Tor amplitude is like a measure of twistiness in a mathematical object. And by imposing a specific condition on the Tor amplitude, we isolate those perfect complexes that are truly simple and fundamental.
Okay. I think that recap definitely helps set the stage for our deep dive into the proof of theorem 5.2.
Okay.
So now the theorem, it claims that a smooth and proper rigid analytic variety is algebraizable if and only if its category of perfect complexes is also smooth and proper.
Correct. And the proof is very meticulously constructed. Each step is carefully laid out.
Okay.
The authors first kind of establish a crucial link between our rigid analytic variety X and the moduli stack of its simple perfect complexes.
Okay.
And so they do this by constructing this special map from X into the coarse moduli space of its simple perfect complexes.
Right.
And this map, which is denoted by alpha, turns out to have some really remarkable properties. It's both injective and atal.
Right. So injectivity, that ensures that the map doesn't collapse any points, right?
Exactly.
So each point in X is mapped to a unique point in the coarse moduli space.
Right.
So it's kind of like this faithful guide, right?
Exactly.
Ensuring that no information is lost during that mapping process.
Yeah, and the atal property, it's a little bit more technical, but it essentially means that the map locally looks like an open embedding.
Okay. Can you elaborate on that a little bit? Like, what does it mean for a map to locally look like an open embedding?
Okay. Imagine you have two spaces. We'll call them A and B.
Right.
And we have a map from A to B. So the map is atal if for every point in A, there exists a neighborhood around that point that looks exactly like an open set in B.
So it's like zooming in on a map, right?
Right.
At a very local level, the map looks like this simple inclusion, kind of preserving that local structure of the space.
Exactly. And this atal property is crucial because it ensures that the map alpha preserves essential geometric information about our rigid analytic variety, X.
Okay. So we have this special map alpha that embeds X into the coarse moduli space of its simple perfect complexes. So how does this help us prove the theorem?
Right. So this embedding connects X to the algebraic world of moduli stacks.
Okay.
And so by showing that the image of X under this embedding is a Moishezon space, the authors essentially bridge the gap between the analytic and algebraic realms.
Okay. Let's pause for a moment and kind of delve into these Moishezon spaces a little bit.
Sure.
So what are they, and why are they important in this proof?
Okay. So Moishezon spaces, they're a special class of complex analytic spaces. They're actually named after Boris Moishezon, a Russian mathematician who made significant contributions to algebraic geometry.
And what makes these spaces so special?
Well, what distinguishes Moishezon spaces from other complex analytic spaces is that they're algebraic in a certain sense. They can be constructed by gluing together pieces of algebraic varieties.
So they provide this kind of bridge between the analytic and algebraic worlds, right?
Exactly. They have just enough meromorphic functions to allow us to connect them to algebraic geometry. And the key point here is that every Moishezon space can be algebraized.
Okay, so if we can show that the image of X under our map alpha, right, is the Moishezon space, then we can conclude that X itself is algebraizable.
Exactly. And that's precisely what the authors do. So by carefully analyzing the properties of the map alpha and the coarse moduli space, they demonstrate that the image of X satisfies the conditions for being a Moishezon space.
So the proof is, it's this beautiful tapestry, right?
It is.
Weaving together concepts from all these different areas of mathematics. Category theory, algebraic geometry, complex analysis, right?
Yeah.
To establish this profound connection between algebraization and the properties of perfect complexes.
Yeah, it's a real testament to the power of abstract mathematical thinking and how these different mathematical fields are so interconnected. It's not just these isolated islands of knowledge.
Okay, so we've discussed theorem point 2 in great detail.
Right.
But the paper, it doesn't stop there, does it?
No, it doesn't.
It also explores this world of formal schemes.
Yes.
Right. And uncovers some really surprising results.
It does.
So remember, formal schemes are like these completions of algebraic objects, right?
Right.
They allow us to study geometric objects in a more like local way, focusing on like neighborhoods of points.
Precisely.
And the paper shows that this connection between algebraization and perfect complexes, it also holds for formal schemes.
It does. So theorem 3.12, it states that a smooth and proper formal scheme is algebraizable if and only if its category of perfect complexes is also smooth and proper.
So it's like this parallel universe, right?
Yeah.
Where the same principles apply, but there's some interesting twists.
Precisely. And the proof of theorem 3.12 follows a similar strategy to that of theorem point 2, but with some technical adaptations to account for the unique properties of formal schemes.
But the paper goes even further, doesn't it?
It does.
It shows that for formal schemes, the smoothness of the category of all coherent sheaves is actually a stronger condition than algebraizability.
Right. So theorem 3.20, it states that if a proper formal scheme has a smooth category of coherent sheaves and its rigid generic fiber is smooth, then the formal scheme must be algebraizable. So this result highlights a subtle difference between formal schemes and ordinary schemes.
Oh, okay. So in a sense, the paper is revealing these like limitations of the formal world, right?
It is.
So just because a formal scheme has this smooth category of coherent sheaves, it doesn't automatically guarantee that it can be neatly completed to an algebraic object.
Exactly. It's like trying to fit a square peg into a round hole. Right. Sometimes it works and sometimes it doesn't. And the category of perfect complexes kind of provides the right level of granularity to discern when algebraization is possible in this formal setting.
This is all incredibly fascinating, but I'm starting to feel like we're reaching the limits of my mathematical scuba gear here. We've explored so much depth already, and I need a moment to kind of process all these intricate connections.
I understand. We've covered a lot of ground today, but I believe the journey has been worthwhile. By diving deep into these technical details, we've gained this much richer understanding of this profound connection between algebraization and perfect complexes.
You're right. And the journey isn't over yet.
No.
We still have the final part of our deep dive to go, where we'll unpack the implications of this groundbreaking work and kind of explore the questions it raises for future research. But for now, let's give our listeners a chance to absorb everything we've discussed so far.
Absolutely.
We'll be back soon with part 3. Welcome back to the final part of our deep dive. I hope you're ready for this grand finale, where we'll unpack the implications of this groundbreaking work and kind of see how these seemingly abstract mathematical concepts can have, such profound and far-reaching consequences.
You know, it really is remarkable how the authors of this paper have kind of woven together all these different strands of mathematics, category theory, algebraic geometry, and complex analysis,
Yeah.
to create this beautiful and insightful tapestry.
Exactly. And in parts 1 and 2, we explored these core concepts of algebraization, perfect complexes, moduli stacks, and the crucial role of Tor amplitude.
Right.
In identifying those fundamental simple objects. And we also delved into the proof of theorem 0.2, which establishes this remarkable link between the algebraizability of a geometric object and the properties of its corresponding category of perfect complexes.
And we saw the authors, so ingeniously use this special map, which is denoted by alpha, to embed a rigid analytic variety X into the coarse moduli space of its simple perfect complexes.
Right.
And this embedding with these remarkable injective and étale properties kind of allowed them to connect X to this algebraic world of moduli stacks.
And then they brought in this concept of Moishazon spaces, these special types of complex analytic spaces that kind of bridge the gap between the analytic and algebraic realm.
Right.
And by showing that the image of X under this embedding is a Moishazon space, they were able to conclude that X itself must be algebraizable.
Right. It's like finding this hidden passageway that connects these two seemingly separate kingdoms.
Right.
And this passageway is paved with this intricate structure of perfect complexes.
Okay, so we've kind of recapped the key points of our journey so far. So now let's shift our focus to the broader implications of this work. So what does this paper tell us about the nature of geometry and its relationship to algebra?
Well, I think one of the most striking takeaways is this profound unity of mathematics.
Okay.
This paper demonstrates that seemingly disparate areas of mathematics, algebra, geometry, analysis, are deeply interconnected.
It's like discovering that different languages with their unique grammar and vocabulary can actually express the same underlying ideas and concepts.
Exactly. And this unity is kind of revealed through this lens of category theory,
Okay.
The category of perfect complexes with its elegant structure and rich properties provides this framework for understanding the subtle interplay between the analytic and algebraic aspects of geometry.
And the paper also highlights, I think, the importance of focusing on the right level of granularity.
Yeah.
So by studying the properties of perfect complexes rather than this broader category of all coherent sheaves, we gain this more refined and insightful perspective on algebraization.
It's like using a microscope with the right magnification, right?
Right.
To see the intricate details of a cell. If we zoom out too far, we lose the crucial information.
Right.
But if we zoom in too close, we might miss the bigger picture.
Okay, so this paper, it deepens our understanding of geometry and its connection to algebra.
Yeah.
But what about its implications for other areas of mathematics,
Right.
and even beyond mathematics?
I think that's where it gets really exciting. So the ideas and techniques developed in this paper have the potential to kind of revolutionize our understanding of a wide range of fields.
Yeah.
From number theory to theoretical physics.
Okay, can you elaborate on that a little bit? Like
Yeah.
how might this work, impact these other areas of research?
Well, for example, in number theory, the concept of algebraization, it plays this crucial role in understanding the arithmetic properties of algebraic varieties. And this paper's results could lead to new insights into the Langlands program,
Yeah.
This vast network of conjectures that connect number theory, representation theory, and harmonic analysis.
Wow, that's quite a leap.
Yeah.
It's amazing how these seemingly abstract mathematical concepts can have such far-reaching consequences.
Right. And in theoretical physics, the language of categories and sheaves is increasingly being used to study quantum field theory and string theory. And so the insights from this paper could potentially shed new light on the geometric foundations of these fundamental theories of the universe.
It's like this ripple effect, with the impact of this work kind of spreading outward to touch all these different areas of knowledge.
Precisely. And that's the beauty of mathematics. You
Yeah.
know, it's this language that transcends disciplinary boundaries, and it has the power to unlock the secrets of the universe.
This deep dive has been this incredible journey,
It has.
taking us to the frontiers of mathematical research and revealing the profound interconnectedness of these different areas of mathematics.
And the journey doesn't end here.
Yeah.
This paper has opened up new avenues for exploration. It's raising these exciting questions that will continue to drive mathematical research for years to come.
So what are like some of the open questions that have kind of emerged from this work?
Well, one intriguing question is whether the results of this paper can be generalized to other types of geometric objects, beyond rigid analytic varieties and formal schemes. So can we find similar connections between algebraization and the properties of appropriate categories of sheaves in other settings?
That's a fascinating question. It seems like there's this whole universe of possibilities waiting to be explored.
Yeah, and another question is whether there are other categories beyond perfect complexes that can illuminate these hidden algebraic structures of geometric spaces. So are there other lenses through which we can kind of view geometry and gain new insights?
These are profound questions that will undoubtedly inspire, future generations of mathematicians.
They will.
And the answers to these questions may lead to new breakthroughs, not only in mathematics, but also in other areas of science and technology.
They certainly could.
Well, on that note, I think we've reached the end of our deep dive.
Yeah.
We've explored the depths of this fascinating paper, uncovering its key insights and far-reaching implications.
It's been a pleasure sharing this journey with you and our listeners, and I hope this deep dive has inspired a sense of wonder and appreciation for the power and beauty of mathematics.
Thank you for joining us. We hope you've enjoyed this exploration of algebraization and its discontents. And remember, the pursuit of knowledge is this ongoing adventure full of unexpected twists and turns, and the rewards are well worth the effort. All right, listeners, ready to dive into something pretty fascinating. We're taking a deep dive into rigid analytic geometry and formal schemes today.
Sounds a bit intimidating, maybe.
Well, it can get pretty complex, but that's why we have you here. We're going to tackle this question that's been around for ages. When can these intricate mathematical objects, these rigid analytic varieties and formal schemes, be algebraized?
Basically, when can we represent them with simpler algebraic structures?
Yeah, exactly. And leading our deep dive today is a paper by Matteo Montagnani titled Algebraization of Rigid Analytic Varieties and Formal Schemes via Perfect Complexes. I am particularly interested in how he ties the smoothness of a mathematical object to its ability to be algebraized.
Ah, yes. That connection is fundamental to Montagnani's research.
Okay, before we get too deep, can we quickly revisit what smooth and proper actually mean in this context? I know we've touched on this before, but a quick reminder never hurts.
Sure. In the world of categories and algebras, smoothness really refers to how well-behaved an object is when we talk about infinitesimal deformations. Imagine a smooth curve in calculus. It doesn't have any sharp corners or sudden jumps.
Right, it's continuous.
Exactly. A smooth object in this context, like a variety or a scheme, will display that same kind of regularity. Now, properness is a little more abstract. It's sort of like compactness, but in a categorical sense. You could say a proper object generally behaves well under morphisms and when we're dealing with limits.
So smoothness is about local behavior, no sharp corners, and properness is more about global structure, how it interacts with its surroundings.
That's a good way to put it.
Now, Montagnani's paper builds on a theorem by Tohen and Vacquier, extending it to non-Archimedean and formal settings. Can you quickly explain that theorem and why this extension is so significant?
Tohen and Vacquier's theorem basically gives us a criterion for when a smooth and proper analytic space, let's say something defined over the complex numbers, can be represented by an algebraic variety. Their work created a bridge between analysis and algebra.
I see.
Montagnani's work seeks to expand that bridge into the realm of non-Archimedean geometry and formal schemes.
Pushing the boundaries, going into even more abstract mathematical landscape.
Exactly. And central to this is the idea of perfect complexes. They're key in his paper.
They're kind of like the blueprint of our mathematical objects, wouldn't you say? Encoding all this essential information about their structure and how they act.
That's a good analogy. At their core, a perfect complex is a chain of maps between objects in a category, usually modules over a ring, and these maps satisfy some specific homological conditions. And these conditions ensure the complex behaves, well, nicely under different operations.
Okay.
They hold a lot of information about the underlying object. And Montagnani shows they're super connected to this question of algebraizability.
Perfect complexes are our key players then. Let's jump into the abstract of Montagnani's paper. The central result, a smooth and proper, rigid analytic variety. It's algebraizable, IF and D, only if its category of perfect complexes is also smooth and proper. It's a two-way street. The properties of the variety are mirrored in the properties of its perfect complexes.
This is where things get exciting. It suggests this very fundamental link between the geometric properties and the categorical properties of these objects.
Like they're inseparable.
Exactly, they're inextricably linked.
This feels like we're on the verge of understanding these mathematical structures much more deeply. But before we go any further, could you explain why this two-way relationship is so important?
It shows how powerful categorical thinking is in algebraic geometry. By focusing on the category of perfect complexes, we gain a new perspective on the fundamental properties of the variety itself. It suggests that being algebraizable isn't just a geometric quirk, but a reflection of a deeper categorical structure.
This isn't just a mathematical curiosity then. It's a brand new lens to view these objects through.
Exactly. And through this lens, we might see new insights and connections that we wouldn't see through purely geometric means.
I'm ready to dive deeper. Let's move on to the introduction of Montagnani's paper. He points to theorem point 2 as his central result, building upon what he laid out in the abstract. So what does this theorem actually tell us?
Theorem point 2 basically formalizes that idea we were talking about. If you have a smooth, proper, and connected rigid analytic variety or formal scheme, it's algebraizable if and only if its category of perfect complexes also has those properties.
So it's the abstract, but now with the full mathematical rigor of a theorem, it's the foundation of the paper.
You could say that. And the proof of this theorem is pretty complex. Montagnier uses a bunch of sophisticated tools, stable infinity categories, derived algebraic geometry, even a theory of Moisezon spaces.
Whoa! Before we get into all that, let's break down the theorem itself. What does connected even mean here, and why do we need it for algebraizability?
Connected, in this context, refers to the geometric notion of connectedness. It means our variety or scheme can't be separated into disjoint pieces.
It's whole.
Right, a cohesive geometric object. The connectedness condition is included because it makes the analysis much easier. We're dealing with a well-behaved object.
So no weird edge cases.
Right. If a variety or scheme isn't connected, trying to algebraize it can get messy. You might end up with multiple algebraic spaces.
Requiring connectedness makes the theorem cleaner.
Exactly. It helps us focus on the core relationship between smoothness, properness, and algebraizability. We can avoid a lot of technical issues that come up with disconnected objects.
Makes sense. Now, the introduction also mentions corollaries point 3 and point 4, which stem from theorem point 2.
Right.
What do these corollaries add?
Corollary point 3 zeroes in on formal schemes. It states that a smooth and proper formal scheme is algebraizable if and only if its category of perfect complexes is also smooth and proper. It takes theorem point 2 and applies it directly to formal schemes, confirming the same relationship holds.
It's like a specific application of the main theorem for formal schemes. What about point 4? It sounds like there's a surprising element there.
Corollary 0.4 delves into the world of bounded derived categories of coherent sheaves on a formal scheme. These categories are closely related to the categories of perfect complexes, but not always the same. And here's the surprising part. This bounded derived category might not be smooth, even if the formal scheme itself is smooth and proper.
Hold on. Even if the object is smooth and proper, the category associated with it might not be. That's a bit unexpected, isn't it?
It is. It highlights that things can get tricky when we move to rigid analytic geometry and formal schemes. Our usual geometric intuition doesn't always apply.
It's a good reminder that these categories can have their own, well, quirks, even when the underlying geometric objects seem straightforward.
Exactly. The interplay between geometry and category theory is full of these unexpected turns.
This is fascinating. Before we get into the specifics of his proof, can you give us a high-level view of the key concepts and strategies Montagnani uses? What are the main ingredients of his approach?
Of course. He uses the power of stable infinity categories, which are fantastic for studying homological algebra.
Right.
And within those categories, he utilizes Morita theory. This is a powerful tool for understanding when two different categories are actually equivalent.
Oh, okay.
This allows him to relate the category of perfect complexes to other categories, ultimately connecting back to the geometric properties of the variety or scheme in question.
Building a chain of connections, bridging the gap between abstract perfect complexes and concrete geometric objects using category theory.
Precisely. And another key piece is the concept of the stack of pseudo-perfect objects. This stack acts kind of like a moduli space, allowing us to organize and study families of perfect complexes.
Okay.
Montagnani looks at the properties of this stack, especially its smoothness and properness, to understand the algebraizability of the variety or scheme underneath.
It's like a map, guiding us through the world of perfect complexes.
Exactly. And then there's the notion of simple objects. They're kind of like the fundamental building blocks of our categories.
Right.
Montagnani adapts this concept to rigid analytic varieties and uses these simple objects to study the structure of these spaces and how they behave under algebraization.
We're on a journey through a mathematical wonderland, it seems.
It's definitely a fascinating journey.
I'm ready to see how he connects all these ideas together. So where do we start?
Well, the paper's structured very logically. He starts by going back to the foundational work of Toan and Vacquier, laying out the groundwork in stable infinity categories and derived algebraic geometry.
Making sure we have a strong base before we start building anything complex.
Exactly. Then he moves into the specifics of non-Archimedean geometry, adapting concepts and techniques from algebra to this new setting. That's where analytification comes into play, the process of going between algebraic and analytic objects.
Analytification, like a Rosetta Stone for deciphering these two mathematical languages.
A perfect analogy. And Montagnani shows that this process is key for understanding how algebraization works in this context.
This is so fascinating. I'm especially intrigued by the role of moishes on spaces. You mentioned them earlier. How do they fit into this?
Moishes on spaces are fascinating. They bridge the gap between rigid analytic varieties and algebraic spaces.
Oh, how so?
They're proper rigid analytic varieties, but with a special structure of meromorphic functions. It gives them this almost algebraic quality.
So they're like a hybrid.
Exactly. And a key result by Brian Conrad showed that non-Archimedean moishes on spaces and proper algebraic spaces are essentially the same, categorically speaking. This equivalence is vital to Montagnani's proof.
So if we can show a rigid analytic variety is a moishes on space,
Yeah.
we've practically proven it's algebraizable.
You got it. And Montagnani demonstrates that when we embed our rigid analytic variety into the coarse moduli space, it actually sits inside a moishes-on space. This is a major step in his argument.
Okay, it's all starting to come together now, like a perfectly executed mathematical dance, all these ideas moving together to reveal the structure and connections underneath.
You could say that.
I can't wait to get into the details. Shall we start with section 1, where Montagnani lays out the groundwork with stable infinity categories and moduli of objects?
Let's do it. We'll unpack those concepts and see how they form the basis for everything else.
Okay, let's dive into section 1, moduli of objects for k-linear stable categories. Stable infinity categories sound pretty wild.
They can be a bit abstract, yeah, but they give us this powerful framework for tackling homological algebra. And that's the language we need to talk about smoothness and properness in this categorical setting.
Right. So can we break this down? What exactly is a stable infinity category? Can you give us an idea of what these categories are and why they're so important for Montagnani's work?
Imagine a category. It's a bunch of objects with arrows connecting them, showing relationships. A stable infinity category takes that idea and, well, expands it tremendously. It's a category where you can take limits and colimits, ways to construct new objects from old ones.
I see.
But it's done in a very complex way. You can also perform homological operations like taking cones and shifts, which are essential when we study chain complexes, things like our perfect complexes.
So it's like a category with like extra abilities.
That's a good way to think about it. And the stable part means these categories have a special structure that makes them behave well under these homological operations.
Okay, so these stable infinity categories are the setting for Montagnani's work. And in this section, he revisits the idea of moduli stacks of objects in these categories, something Toan and Vacquier developed. Can you remind us what moduli spaces and stacks are and how they fit in here?
A moduli space is basically a geometric space. Each point represents a different geometric object of a specific type. You could think of it like a collection of geometric objects with similar traits. A moduli stack takes this idea a step further. It's more flexible, it keeps track of the objects themselves, but also their families and how they change.
So a moduli stack is like a moduli space with a lot more detail.
Exactly. In this case, we're talking about the moduli stack of objects in a k-linear stable infinity category. This means we're working with categories where the arrows have a kind of linearity, which is common in algebraic geometry, where we often work with modules over a field.
And why is this moduli stack of objects so important? What does it tell us?
It holds key information about how the objects in the category are structured and how they behave. Studying it can give us insights into the properties of the category itself.
Okay, that makes sense. Now he brings in this stack called the stack of pseudo-perfect objects. What are those?
A pseudo-perfect object is essentially a functor. It's a map between categories that preserve structure.
Got it.
In this case, it's a functor that preserves perfectness. Remember, perfect complexes are those well-behaved chain complexes we talked about. A pseudo-perfect object takes those perfect complexes in one category and maps them to perfect complexes in another.
So it's like a transporter of perfectness between categories.
That's a great way to put it. And this stack of pseudo-perfect objects, denoted as MC, it turns out to be pretty interesting. Montagnani shows that it's a derived stack, meaning it has this, let's say, homotopical structure. It captures higher-level information about how these objects relate to each other.
MC, our catalog of pseudo-perfect objects. What else do we know about it?
He shows that if the category C is what we call finite type, meaning it's not too big or complicated, then MC is locally geometric. This means that even though it's this super abstract object, when you zoom in on any point, it looks like a familiar geometric object.
So MC is both abstract and concrete at the same time.
Exactly. It's a very multifaceted object, and its properties can tell us a lot about the category C itself.
I'm eager to see how he brings this back to algebraizing varieties and schemes. But let's go to section 2, where things start to feel more concrete. It's called stacks of pseudo-perfect objects in non-Archimedean geometry. What's happening here?
This is where Montagnani takes all that groundwork from section 1 and applies it specifically to non-Archimedean geometry.
Can you remind us what non-Archimedean geometry is all about? How is it different from the geometry we're used to?
In the geometry we usually learn, Euclidean geometry, we measure distances using absolute value. Non-Archimedean geometry uses a different way to measure distance based on a special kind of absolute value.
Okay.
And this results in some unusual, even counterintuitive geometric properties. Like in non-Archimedean geometry, all triangles are isosceles.
All triangles are isosceles. That doesn't sound right.
It's a different set of rules, and it turns out that this non-Archimedean setting is the natural place for rigid analytic varieties and formal schemes, the objects Montagnani wants to algebraize.
Okay, so we're in this world of non-Archimedean geometry now. What does Montagnani do with our moduli stack, MC here?
He creates an analytic version of MC, which he calls ANMC. This new stack is designed specifically for the non-Archimedean world, taking into account the special properties of rigid analytic spaces.
He's translating MC from algebra to non-Archimedean analysis.
Exactly. And he proves a really important result. ANMC is equivalent to the analytification of MC, which is written as man-C.
Okay, hold on. Analytification, is that like turning something algebraic into something analytic?
You got it. It's a process where you start with an algebraic object, like a scheme, and then you associate it with an analytic object, like a rigid analytic space.
Seeing the same thing from two different perspectives.
Exactly. So we have MC, the algebraic version of our stack, and then we have man-C, its analytic counterpart. Montagnani's showing that these two are basically the same thing when we're working with non-Archimedean geometry.
We have a bridge between the algebraic and the analytic.
Right. And it's crucial for understanding how algebraization works here.
Okay, this is getting pretty complex. I notice Montagnani looks at a specific case where C is the category of modules over a smooth and proper algebra called mod B. Why is this case so important?
It's a really good concrete example where we can see how all the ideas from section 1 work. By focusing on a specific category like mod B, he makes those abstract concepts more tangible, showing how they relate to familiar geometric objects.
So it's a way to ground the abstract theory.
Exactly. And in this case, he can give a similar characterization for the stack of simple objects, which we denote as symbene. Remember those building blocks of our categories.
Right, the simple objects.
He's showing that this stack of simple objects also has an analytic counterpart in this category, and it's equivalent to its analytification.
Got it.
To wrap up section 2, he proves another key result. If you have a rigid analytic variety, X, and its category of perfect complexes is smooth and proper, then two stacks and M-perfects and perfects are equivalent.
Whoa, okay. Can we unpack that? What are those stacks and why is this equivalence so important?
Let's start with perfects. That's
Yeah.
the stack of all the perfect complexes on the rigid analytic variety X. It's a way to organize and study all the perfect complexes associated with X. And M-perfects is a bit more complex. It's the analytification of the stack of pseudo-perfect objects in the category of perfect complexes on X. It's basically an analytic version of that stack, but tailored for the specific setting of perfect complexes on X.
So we're taking that general concept of the stack of pseudo-perfect objects, specializing it for perfect complexes on our variety X, and then making it analytic to get n-imperfects.
Exactly. And the big takeaway is that n-imperfects and perfects are equivalent. This connection suggests that the stack of perfect complexes on X, which is a very geometric object, is deeply connected to this more abstract stack of pseudo-perfect objects from category theory.
So it's the same object, but we're seeing it from two different viewpoints, one geometric, one categorical, and they're the same.
Precisely. This equivalence is a stepping stone to the main theorem. It bridges the geometric properties of X and the categorical properties of its perfect complexes.
It's so intricate. But I'm starting to see how it all fits. It's like a giant puzzle, and we're starting to see the picture.
That's a great way to put it. And we're about to see the full picture in section 3, where Montagnani proves his main theorem. Ready for the finale?
Absolutely. Let's see how he puts all these pieces together to prove this amazing link between smoothness, properness, and algebraizability. Okay, we've gone through stable infinity categories, non-Archimedean geometry, all these pseudo-perfect objects. Now, the main event, section 3, the proof of the main theorem. I'm ready to see how it all comes together.
It's a beautiful proof, really well structured, full of clever insights. It just shows how powerful abstract math can be.
All right, let's take it one step at a time. What's the first move in his strategy?
He starts by setting up the problem very carefully. He reminds us that a rigid analytic variety, or a formal scheme for that matter, is algebraizable if it's isomorphic to the analytification of some algebraic space.
So, like finding his algebraic twin.
That's it. And the key to finding that twin lies in smoothness, properness, and the category of perfect complexes.
Right, the core concepts. So how does he link these to the algebraizability problem?
He uses this idea of the coarse moduli space. It's connected to the category of perfect complexes on our variety or scheme.
Okay.
Remember that moduli stack? It keeps track of all those perfect complexes and their families. The coarse moduli space is like a simplified version of that stack. We kind of forget some of the finer details about how those complexes vary.
So it's a more general view.
Yeah, you could say that. And the good thing about the coarse moduli space is that it's often easier to work with than the full moduli stack.
Gotcha. So we have this coarse moduli space, and it's telling us something important about the perfect complexes on our variety. How does he use this to get closer to algebraizability?
He makes a special map and embedding from our rigid analytic variety or formal scheme into this coarse moduli space.
An embedding.
Right. It means our variety or scheme is basically sitting inside this coarse moduli space in a way that preserves its geometric structure.
Like fitting it in perfectly.
Exactly. And here's the brilliant part. He proves that this embedding ends up inside a special kind of space called a Moisezon space.
Ah, Moisezon spaces. They have that almost algebraic quality, right?
That's right. They're these proper rigid analytic varieties that have a lot of meromorphic functions, which brings them close to algebraic spaces.
Right.
And remember Brian Conrad's theorem? It basically said non-Archimedean Moisezon spaces and proper algebraic spaces are essentially the same thing, category-wise.
Right, right. So if our variety fits into a Moisezon space, it's almost there in terms of being algebraic.
That's the crucial point. By showing our variety sits inside a Moisezon space, he links it directly to algebraic spaces.
Okay, that's making sense. But how does he actually prove the embedding lands inside a Moisezon space? Can we go through that?
Of course. It's a little technical, but the main idea is this. He uses those properties of smoothness and properness. Remember, we start with a rigid analytic variety, or formal scheme, that's smooth and proper, and D, its category of perfect complexes, is also smooth and proper.
The two main conditions.
Exactly. He uses those properties to show that where our variety sits in the coarse moduli space, that part also inherits those same properties.
The good behavior carries over.
Precisely. And then he uses this really neat trick. There's a theorem that says any smooth and proper analytic space that's also projective, it basically means it can be embedded into a projective space, has to be a Moisezon space.
Okay.
And he shows that the image of our variety does meet that projectivity condition. That's where the fact that the category of perfect complexes is smooth and proper is so important.
So smoothness and properness of the variety lead to smoothness and properness of the image, which leads to projectivity, which means it's a Moisezon space.
Perfectly put. He's achieved what he set out to do. He's shown our rigid analytic variety can be embedded into a Moisezon space.
And since those are basically the same as algebraic spaces, we've shown our original object can be algebraized.
It's like magic, but with rigorous logic instead of tricks.
This has been an amazing journey. We've covered some pretty tough math, but it's been worth it. We've seen how Montagnani's work connects analysis, algebra, and category theory in such a deep way.
It really shows how interconnected mathematics is.
Before we finish up, I want to touch on one more thing, the role of simple objects. You mentioned they're kind of like building blocks for these categories. How does Montagnani use them in the proof?
He uses them to explore the structure of the rigid analytic variety or formal scheme.
Right.
Remember, a simple object is like a basic, irreducible element of a category. If we understand how these simple objects behave under algebraization, we can learn something about how the more complex objects they make up will behave.
Like studying atoms to understand molecules.
Exactly. And he shows that whether a simple object can be algebraized is directly tied to the smoothness and properness of the category of perfect complexes. This connection gives us even more insight into the main theorem.
This is all so fascinating. We could probably spend hours talking about this paper.
I know, right? It's one of those papers that really makes you think.
And I bet it'll inspire lots of new research in the future, pushing the boundaries of algebraization even further.
Absolutely. There are so many questions left to explore.
Well, on that exciting note, let's wrap up this deep dive. It's been a truly fascinating exploration.
A great example of how powerful and beautiful modern mathematics can be.
This is The Deep Dive. Signing off. Until next time, keep exploring. All right, let's jump right in, shall we? Today, we're diving into some pretty abstract math, the kind of stuff that makes your brain do backflips. We're talking about when certain geometric objects are algebraizable.
It's a fascinating question for sure.
And of course, we'll try to connect it to the idea of smoothness. It's like we're using algebra to crack open geometric secrets. I've got an expert with me today who can navigate this wild territory, ready to guide us.
Absolutely. Let's dive in.
So, first things first, can you give us the lay of the land? What are the big players here? Things like rigid analytic varieties and formal schemes. They ring a bell, but I'm a little fuzzy on the specifics.
Okay, well, rigid analytic varieties, you can kind of think of them like the complex analytic versions of algebraic varieties, but they're defined over fields with a non-Archimedean absolute value.
Ah, okay. And the main examples are spaces where the functions are a quotient of the Tate algebra, right?
Exactly.
And for those who are like, Tate algebra, what's that? It's basically power series that converge in a special way,
Yeah.
specifically with respect to the Tate norm. Okay, so we have those, and then formal schemes. What about them?
Right, formal schemes, they're kind of like schemes, but we build them from completions of rings. They give us a way to look at the infinitesimal neighborhoods of points in algebraic geometry.
Okay, so both of these, rigid analytic varieties and formal schemes, they're both ways to do geometry over fields with a special kind of absolute value, like the pair-addic numbers, which are a whole different animal compared to the usual real numbers most people are used to.
Exactly. The pair-addic numbers have a different way of measuring closeness, or distance, right? Instead of using decimals, we use powers of a prime number.
Yeah, very different intuitions. Definitely not your typical Euclidean geometry. So we've got these spaces, but then there's this whole question of algebraizing them. What does that even mean?
That's the heart of the algebraization problem. When can we realize a rigid analytic variety or a formal scheme as the analytification of an algebraic space? That's the big question.
I gotta be honest, that sounds super abstract. Why should we even care about algebraizing these objects? What's the point?
Think of it like this. Imagine you're studying a complicated shape, but you can only look at its shadows.
Okay, I'm intrigued.
Algebraization is like figuring out if you can reconstruct the original shape from its shadows.
I like that analogy. So, like, if I see this shadow of a cube, I know it could be a cube, but it could also be other shapes that cast the same shadow.
Exactly. It's a general problem that pops up in lots of areas of mathematics.
And how does smoothness fit into all of this?
That's where the category of perfect complexes comes in.
Okay, perfect complexes. Vaguely familiar, but I need a refresher.
Well, essentially, they're complexes of sheaves that are well-behaved in a precise sense. Locally, they look like vector bundles.
Right, vector bundles. Okay, that's coming back now. So how do these perfect complexes help us determine if something can be algebraized? It seems like we're jumping from geometry to something much more abstract.
The cool thing is we can define what smoothness means for these categories of perfect complexes. It's all about how objects in the category vary or deform.
Okay, so it's a different kind of smoothness than we usually think about in geometry.
Exactly. And there's this amazing theorem by Towen and Vacchi that links the algebraizability of a complex analytic space to the smoothness of its category of perfect complexes.
So are they saying if the category is smooth, then the space itself can be algebraized?
Pretty much, yeah. It's an amazing connection. And the paper we're looking at today, it takes us even further and generalizes Towen and Vacchi's theorem to the non-Archimedean and formal settings.
That sounds like a serious mathematical feat. What were some of the challenges they faced? What did they have to figure out to do that?
One big thing was redefining what simple objects mean in this more general derived setting. Then they had to work with the analytification functor, which is kind of like a bridge between the algebraic world and the analytic world.
So lots of translating back and forth between different languages.
Yeah, it was tough. They even brought in non-Archimedean Moisezon spaces, which are kind of like the non-Archimedean version of projective varieties.
Non-Archimedean Moisezon spaces. Sounds like something out of Star Trek.
Ha, a little bit.
Okay, so after all that work, what was their main result? What did they actually prove?
They proved that if you have a smooth, proper, and connected rigid analytic variety, or a formal scheme, it can be algebraized if and only if its category of perfect complexes is also smooth and proper. It's a powerful extension of Towen and Vacchi's work.
So now we have this new tool to tackle the question of algebraization. It's mind-blowing how they used category theory to solve a geometric problem.
And there's more. They also dug into when certain categories of sheaves on formal schemes are smooth, showing that some things that are true in algebraic geometry don't carry over to the formal setting. So there are definitely surprises lurking in the formal world.
Oh, I'm sure there are. I'm ready to dig into the details. This paper is dense, so lead the way. Where do we start?
A good place to start would be their proof of the equivalence between the derived stack of simple perfect complexes and the analytification of the moduli of objects. That's a core part of their algebraization theorem.
Okay, let's do it. Walk me through it.
So they use perf_sum(x) to denote the derived stack of simple perfect complexes, and then for the analytification of the moduli of objects, they write mipsim perfx n mn. They want to show these two are equivalent.
So we're working with derived stacks, which most of our listeners are probably familiar with. We're essentially considering our spaces as stacks and working in a derived setting so we can do homological algebra. A lot of folks might be used to thinking about schemes, but stacks are much more natural when you're dealing with moduli problems like we are here. And we're focusing on perfect complexes, which are like the nicest complexes of sheaves you can have in this derived setting.
Exactly. The notation might seem a little intimidating, but the ideas are super elegant. To prove this equivalence, they start by looking at the functor of points of the analytification of the stack msim. This functor is denoted by g, y, where y is a derived algebraic stack. It helps us see how algebraic ideas show up in the analytic world.
Okay, so this functor g is like our translator, right?
Yeah.
Helping us move between algebraic and analytical concepts.
Right. And Holstein and Porta proved this key theorem in derived analytic geometry that tells us if you have a well-behaved derived algebraic stack, you can understand its analytification through this functor, gy.
What does well-behaved mean in this context? Probably something technical.
It means the stack is locally geometric and locally almost of finite presentation. These conditions make sure our stack isn't too wild or unmanageable.
So we use G to translate from the algebraic stack to its analytic counterpart. How does that help us with the equivalence between perf_sum(x) and perf_sum(pax)?
The magic happens when we apply this functor to a specific stack, MC, where C is a smooth and proper category in PRL. That's a world of presentable, compactly generated infinity categories. What we find is that the functor of points of the analytification of MC, which is written as man_C, is equivalent to another stack, ANMC, which is built directly in the analytic setting.
So we're showing that these two stacks, one from the algebraic world and the other from the analytic world, are actually describing the same mathematical objects.
Exactly. It's like finding a hidden passageway between two separate worlds. And this equivalence also respects the idea of simple objects. It gives us an equivalence between porsim B and msim, where B is a smooth and proper algebra.
Just to make sure I'm following, simple objects are like the fundamental building blocks of our categories, the things we can't break down further. And this equivalence tells us that we can identify those simple objects in both the algebraic and analytic settings.
You got it, like finding out that the same basic particles make up both stars and atoms.
Okay, I'm with you. Now, you mentioned something about Tate acyclicity being involved in this equivalence. Can you remind me how that fits in?
Tate acyclicity is super important in connecting those algebraic and analytic descriptions of the stacks. It gives us a way to translate between perfect complexes over a derived affinoid algebra and perfect complexes over the corresponding affinoid space.
So Tate acyclicity is like another translator, making sure everything is consistent between these two different viewpoints.
Exactly. And if we carefully analyze how Tate acyclicity interacts with those simple objects, we can show that this equivalence between stacks preserves that crucial property. It's like making sure our translator isn't losing any subtle nuances when switching between languages.
That makes sense. We're not just going for some abstract equivalence. We need to make sure it captures the details that matter for understanding algebraization. Okay, so now we've got this equivalence. How do the authors use it to actually prove their main result, the algebraization theorem for these smooth, proper, and connected rigid analytic varieties?
That's where things get really exciting. The proof has two main parts. First, they show that there's an embedding of the rigid analytic variety, which we can call X, into the coarse moduli space of the analytification of nissim, perfx, which they denote by man X. This embedding needs to be both injective, meaning it doesn't collapse any points, and étal, which means it preserves the local structure.
Injective and étal. So kind of like a well-behaved map on a globe that doesn't tear or fold the surface.
Precisely. They construct this embedding by making a map from X to perf X, which assigns the skyscraper sheaf at that point to each point in X.
Right. Skyscraper sheaves, those are our perfect complexes concentrated at a single point. So it's like putting a unique mathematical beacon at each point. But why does that map factor through the stack of simple objects?
Because skyscraper sheaves are themselves simple objects. They're the most basic building blocks in the category of perfect complexes. And when they look closely at this map, they show that it gives us an injective and étal map into the coarse moduli space, which is exactly what we need.
Got it. So we've embedded our space into this moduli space. What's next? How do we get to algebraization from there?
Here's where they bring in those Morchazon spaces. They're special types of rigid analytic varieties that are, in a way, close to being algebraic.
Ah, yes. The missing link between the analytic and algebraic worlds.
Right, and Conrad has a key theorem that says a rigid analytic variety is a Morchazon space if and only if it comes from the analytification of a proper algebraic space.
So if our space is Morchazon, we know it has algebraic roots.
Yeah.
It's like a test for algebraicity.
Precisely. And the authors use this theorem to show that our rigid analytic variety X is indeed algebraizable. They prove that the embedding of X into the coarse moduli space, man X, actually puts X inside an open subset that's the analytification of an algebraic space.
So X gets caught in the algebraic net of this Morchazon space.
Yeah.
How do they prove that this open subset is actually Morchazon, though? That seems like it would require some deep knowledge of those spaces.
You're right, it gets quite technical. They have to analyze the tangent spaces of the coarse moduli space using tools from derived algebraic geometry and growth-endic duality.
Tangent spaces, those are like the local linear approximations of our space, right? Like when we draw maps of the Earth, we're using a flat approximation.
That's a good analogy. And by looking at these tangent spaces, they show that the dimension of X matches the transcendence degree of its field of meromorphic functions. And that's a key property of Morchazon spaces.
Meromorphic functions, right? Those are like fractions of holomorphic functions. They behave nicely in the complex world, except maybe at a few isolated points.
Exactly. And because the dimensions match, we know that our open subset is a Morchazon space. And since X is embedded in this Morchazon space, it inherits that property, meaning it must be algebraizable.
Wow, it's like a chain reaction of logic. We start with the equivalence of those stacks, then we embed our space into a moduli space, and finally we use Morchazon spaces to prove algebraizability. Pretty incredible. But wait, they don't stop there, right? They also tackle algebraization in the world of formal schemes. Can you give us a sneak peek at what they do there? What are the main ideas and challenges?
Absolutely. But I think this is a good stopping point for now. Let's let all of this sink in first. Then we can dive into the formal scheme world and see what surprises are waiting for us.
Okay, you've convinced me. I need a moment to process all of this. To our listeners, we'll pick up right where we left off, so don't go anywhere.
Welcome back. I bet you're ready to hear about formal schemes.
Oh, absolutely. That was quite a trip through stacks, moduli spaces, and those mysterious Moishazon spaces.
I'm ready for more. So, what's the deal with formal schemes? How does algebraization change in that context?
Well, when we move to formal schemes, things get a little more complicated.
Mhm.
Remember, formal schemes are built from completions of rings, which means we're adding in these infinitesimal elements. It lets us look at geometry in a super fine-grained way.
Okay.
But it also means some of the tools we use in algebraic geometry don't quite work the same way.
So even though we're still in the world of schemes, this completion process throws a wrench into things.
Exactly. One of the challenges is that some results about smoothness, which are pretty straightforward in regular algebraic geometry, get a lot more subtle with formal schemes.
I see. So how do the authors deal with that? How do they connect algebraization in the rigid analytic world to algebraization in the formal world? They prove this really neat theorem that links the algebraizability of a formal scheme to the algebraizability of its rigid generic fiber. Basically, if we can move from the rigid analytic world down to the formal world, and we keep things smooth and proper along the way, then our formal scheme has to be algebraizable too.
So we're using what we know about algebraization in the rigid analytic setting as a guide for figuring out what's happening in the formal setting.
That's a great way to think about it. And they also use a powerful result from Thomason and Trobow, which tells us how to break down the category of perfect complexes over the ring of integers of our non-Archimedean field.
Break down the category, like decompose it into smaller pieces.
Yeah, exactly. It lets us focus on the parts of the category that matter for algebraization, kind of like sifting through sand to find the gold.
Makes sense. So by zeroing in on these key parts, we get a better understanding of how algebraization works in the formal world. Can you tell me a little more about how that decomposition helps them?
Sure. By carefully analyzing the pieces, they find a connection between the perfect complexes on our formal scheme and the perfect complexes on its rigid generic fiber. And that connection, combined with the theorem about going from the rigid analytic world to the formal world, lets them carry over algebraizability between the two.
It's like they built a bridge between those two worlds.
Precisely. It shows how powerful abstract reasoning can be and how connected different areas of math really are.
This is incredible. But you mentioned earlier that looking into formal schemes led to some weird discoveries about coherent sheaves. What did they find that was so strange?
One of the big surprises is that, unlike in classical algebraic geometry, the category of coherent sheaves on a formal scheme isn't always smooth.
Hold on. Coherent sheaves, those are like the instructions for building structures on our spaces, right? And you're saying those instructions don't always change smoothly in the formal world.
It seems counterintuitive, but the formal world has its own rules, remember. They actually have a counterexample, a specially made formal scheme that has a smooth, rigid, generic fiber, but its category of coherent sheaves isn't smooth.
So even if the rigid generic fiber is well behaved, the formal scheme itself can still have this hidden roughness in its coherent sheaves.
Yeah, it's like looking at a perfectly smooth surface under a microscope and realizing it's actually super rough at a tiny scale.
I see. This is fascinating. I'm guessing this has some important implications. In algebraic geometry, smoothness is usually a good sign. It often tells us something about the geometry of the space itself.
Exactly. And what this paper shows is that in the formal world, that connection between the smoothness of the space and the smoothness of the category of coherent sheaves breaks down. It really highlights how different these two settings are.
Wow, so even something as basic as smoothness can act differently depending on the context. It makes you appreciate how deep these ideas are.
Absolutely. This paper is a perfect example of how exploring abstract ideas can lead to a deeper understanding of the geometry behind them. It shows that even the most familiar ideas can have surprises when you look at them from a new angle.
This is a lot to absorb. What are the most important takeaways from this paper? What should our listeners really remember?
I think the biggest takeaway is that these seemingly abstract ideas, like the smoothness of a category, can have huge implications for real geometric problems. The authors show how these abstract tools can be used to solve problems that were really tough to crack before.
It really shows how powerful abstract thinking is and how beautiful math can be.
It does, and it also shows that making connections between different parts of math is so important. The most exciting results often come from bridging the gaps between areas that seem completely separate.
I totally agree. This has been an incredible journey. I'm still trying to wrap my head around everything, but I'm starting to see the bigger picture. Anything else we need to cover, or are we good to move on?
I think we've hit the main points. Of course, there are always more details, but this should give you a good feel for the key ideas and the beauty of this area of math.
Sounds good to me. This paper has definitely given me a lot to think about. Okay, listeners, we're going to wrap up this episode of The Deep Dive. We hope you enjoyed this exploration as much as we did. All right, we're back. Whew, that was intense, even for me. I'm still thinking about those coherent sheaves and how they can be so weird in the formal world. It's like finding out gravity works differently on Tuesdays.
It's definitely a surprising result, that's for sure. It really shows how strange things can get in the formal setting.
Totally. So where do we go from here? What else did the authors look at in this paper?
Well, they didn't stop at just those surprising facts about coherent sheaves. They actually used what they learned to prove some really interesting things about algebraization.
Okay, so they were still able to make progress on the algebraization problem, even with all those twists and turns in the formal world.
Oh, yeah. They're brilliant mathematicians. They use this idea of a derived formal analytic space.
Derived formal analytic space. It's a mouthful. What exactly is that?
Think of it as a kind of combination of a formal scheme and a rigid analytic space. It captures both the infinitesimal stuff from the formal scheme and the analytic stuff from the rigid analytic space.
So it's like a hybrid space, getting the best of both worlds.
Exactly. And the authors show that under the right conditions, you can actually algebraize these derived formal analytic spaces.
Wait, so they're not just algebraizing formal schemes or rigid analytic varieties. They're algebraizing these hybrid spaces that combine the two.
You got it. And that turns out to be really useful. It lets them prove a very general algebraization theorem for formal schemes that have certain smoothness conditions.
Okay, my brain is starting to hurt. Can you break that down a little bit? What are these smoothness conditions? And how does algebraizing these hybrid spaces help them prove the theorem for formal schemes?
Sure. The smoothness conditions basically make sure that the formal scheme is well-behaved from an analytic point of view. They're technical, but they ensure that the rigid generic fiber of the formal scheme is also smooth.
So it's like these conditions force the formal scheme and its rigid generic fiber to get along.
Exactly. And remember earlier we talked about how they proved that the algebraizability of a formal scheme is connected to the algebraizability of its rigid generic fiber.
Yeah, if you can move from the rigid analytic world to the formal world without messing up the smoothness, then the formal scheme is algebraizable.
Right. So by using these smoothness conditions, they can apply that theorem. And algebraizing the derived formal analytic space provides the connection between the rigid analytic world and the formal world.
I think I'm starting to see the whole picture. It's like a jigsaw puzzle where you need all the pieces to see what it really is.
Great analogy. And the authors have done a fantastic job putting all these pieces together to prove this really powerful algebraization theorem.
This is groundbreaking stuff. I have to admit, though, I'm a bit overwhelmed. What do you think the authors are trying to tell us with this paper? What's the big takeaway?
I think they're showing us that the world of formal schemes and rigid analytic varieties is full of surprises. It's a place where our usual geometric instincts might not be right, but we can still find some really beautiful mathematical truths.
You said it perfectly. This paper has really opened my eyes. It makes me want to learn more about these areas of math.
Me too. And I think it also shows how powerful abstract thinking can be. Sometimes, to understand something concrete, you have to step back and look at it from a more abstract angle.
Couldn't agree more. I think we've covered this paper pretty thoroughly. It's been a long journey, but I feel like we've come to a better understanding of these amazing concepts.
I agree. It's been a lot of fun exploring this with you.
The pleasure was all mine. And to everyone listening, thanks for joining us on this deep dive. We hope you learned something new, and maybe even feel inspired to explore the world of formal schemes and rigid analytic varieties yourself. Until next time, keep those mathematical minds working. All right, let's dive into this. This paper by Matteo Montagnani,
Matteo Montagnani.
Algebraization of rigid analytic varieties and formal schemes via perfect complexes.
Yeah.
It's a mouthful.
It is.
But we're dealing with some pretty high-level math here.
Yeah.
Exploring when these complex geometric objects, rigid analytic varieties and formal schemes, can be represented by simpler algebraic structures.
Absolutely. It is a deep dive into the interplay between algebra and geometry. We're essentially trying to figure out when we can find an algebraic blueprint for these spaces,
Right.
a way to describe their properties using, the language of polynomials and equations.
And the key tool in this investigation is the concept of perfect complexes, right?
Yes.
I'm curious to understand how these mathematical objects help bridge the gap between geometry and algebra.
Perfect complexes are indeed very powerful. They allow us to study the geometric properties of these spaces by examining their local behavior, meaning how things change in tiny neighborhoods around each point. And what's remarkable is that these local properties, which are encoded in the perfect complexes, can actually reveal whether a global algebraic structure exists for the entire space.
So it's like analyzing the fine-grained details to understand the overall structure.
Exactly.
Can you give us a bit more intuition about how these perfect complexes are constructed?
Sure.
What kind of information do they capture?
So perfect complexes are built from sheaves,
Right.
which you can think of as ways of assigning data to each point in our space.
Okay.
And these data can be algebraic objects like rings or modules. And by studying how they change as we move from point to point, we gain insights into the geometry of the space.
I see. So it's like attaching labels to each point, but the labels themselves can be quite complex and carry a lot of information. And the paper focuses on a specific property of these perfect complexes called smoothness. Why is that property so crucial for algebraization?
So smoothness in this context, in the context of perfect complexes, indicates that the space is well behaved at a local level. It means there are no sharp corners or singularities, and everything changes smoothly as we move around. And this smoothness property often reflects the existence of an underlying algebraic structure.
So smoothness of the perfect complex suggests the possibility of finding a nice, clean, algebraic description for the geometric space.
Exactly. And the paper explores this connection in detail, providing specific criteria for algebraization based on the properties of these perfect complexes.
Now, the paper deals with two types of geometric objects, rigid analytic varieties and formal schemes. Are there any key differences in how algebraization works for these two?
Yeah, that's an important point. While smoothness of perfect complexes strongly suggests algebraizability for rigid analytic varieties, the story is a bit more subtle for formal schemes.
Can you elaborate on that? What makes formal schemes different in this context?
So formal schemes arise when we want to study a geometric space with an added layer of infinitesimal information. Imagine zooming in infinitely close to a point on a curve. A formal scheme captures not only the point itself, but also how the curve is bending and twisting at that point.
So formal schemes provide a more refined view of the geometry,
Yes.
incorporating these infinitesimal details. How does that impact algebraization?
The presence of these infinitesimals adds complexity to the picture. While smoothness of perfect complexes still plays a role, it doesn't always guarantee algebraizability for formal schemes.
That's fascinating. So even with this powerful tool of perfect complexes, algebraization isn't always straightforward,
Right.
especially when dealing with the intricacies of formal schemes.
Precisely. And one of the surprising findings in the paper is that even if a related category called cobex, which consists of certain types of sheaves on the formal scheme, is smooth, it doesn't necessarily imply that the formal scheme itself is algebraizable.
That's a bit counterintuitive. Can you unpack that a bit more? Why is the smoothness of codex not a guarantee of algebraizability?
It highlights a fundamental difference between formal schemes and their classical counterparts, regular schemes. In the world of regular schemes, smoothness of cobex is often equivalent to algebraizability.
Okay.
However, the presence of those infinitesimal details in formal schemes creates a situation where this equivalence breaks down.
So we're seeing a subtle but crucial distinction between these mathematical worlds.
Yes.
And even with sophisticated tools, there are still some mysteries to unravel.
Absolutely. And this is what makes the paper so intriguing. It pushes the boundaries of our understanding of algebraization and reveals some unexpected differences between rigid analytic varieties and formal schemes.
Before we dive into the details of the paper's results, can you remind us what these mathematical objects, rigid analytic varieties, and formal schemes actually are? What makes them so special, and why are we interested in their algebraization?
Sure. Let's start with rigid analytic varieties. They are geometric objects defined over a special type of field called a non-Archimedean field. Unlike our familiar real or complex numbers, non-Archimedean fields have a different notion of distance, where the triangle inequality doesn't hold in the usual way.
A different notion of distance.
Yes.
Can you give us an example of how that works?
Sure. Imagine you're working with the p-adic numbers, a classic example of a non-Archimedean field. In this world, two numbers are considered close if their difference is divisible by a high power of the prime number p. So numbers like 1 and 1 plus p to the 100 would be extremely close, even though they might seem far apart in our usual way of thinking.
That's fascinating. So it's like a different way of measuring proximity
Right.
based on divisibility rather than absolute value.
Exactly. And this unusual notion of distance gives rise to a whole new type of geometry called rigid analytic geometry. And rigid analytic varieties are the geometric objects we study in this setting. They have some intriguing properties that set them apart from their classical counterparts.
So it's a different kind of geometry built on these unusual fields. Why are we interested in their algebraization? What does it mean for a rigid analytic variety to be algebraizable?
It means we can find an algebraic variety, a space defined by polynomial equations that captures the essence of the rigid analytic variety. It's like finding a simpler, more concrete representation of the space using the familiar language of algebra.
I see. So it's about connecting this exotic, non-Archimedean world to the more familiar realm of algebraic varieties.
Yeah.
What about formal schemes?
Yeah.
How do they fit into the picture?
Formal schemes are a bit more abstract, but equally important. Imagine you have a geometric space, and you want to study its local structure around a particular point. You can zoom in infinitely close to that point, and the formal scheme captures not only the point itself, but also all the infinitesimal information around it.
It's like having a superpowered magnifying glass that reveals the hidden details of the space at that point.
Precisely. And just like with rigid analytic varieties, we can ask whether a formal scheme is algebraizable. In this case, it means we can find an algebraic scheme, a more general type of space defined by algebraic equations that completes the formal scheme, capturing all those infinitesimal details.
So in both cases, algebraization is about finding a simpler, more concrete representation of these complex geometric objects. It's about bridging the gap between the abstract world of geometry and the more familiar world of algebra.
Exactly. And this bridge is built using the powerful tool of perfect complexes. By studying their properties, particularly smoothness, we gain insights into whether and how these geometric objects can be algebraized.
This is already getting very interesting. I'm eager to dive into the details of the paper and explore how those algebraization criteria actually work.
I'm ready to delve in when you are.
Let's do it.
It's a fascinating exploration of deep connections between algebra and geometry.
Okay, so we've established that perfect complexes are key to understanding algebraization.
Yes.
But how do we actually use them? What is the process of analyzing these complexes and checking for smoothness look like?
Well, one powerful tool for analyzing perfect complexes is the cotangent complex.
Yeah.
And it provides information about how a space is deforming or changing infinitesimally. You can think of it as a generalization of tangent lines to a curve, but in a more abstract, higher dimensional setting.
So it's like a measure of how the space is bending at each point,
Yes.
but in a more sophisticated way.
Exactly. And a key property of smooth spaces is that their cotangent complexes have a very specific structure. They are perfect, meaning they have finite length, and satisfy certain technical conditions related to duality and tensor products.
So we're looking for a perfect cotangent complex
Right?
as a sign of smoothness, which in turn suggests the possibility of algebraization.
Precisely. Now, the paper dives deep into specific criteria for checking the smoothness of perfect complexes in both the rigid analytic and formal scheme settings. And these criteria are essential to the paper's main results.
Can you give us a taste of those criteria? What are some of the key ideas involved in checking for smoothness?
One important technique is to analyze how perfect complexes behave under base change. Imagine you have a map between two geometric spaces. Base change allows us to pull back geometric objects like sheaves or perfect complexes from one space to another.
So it's like transferring data from one map to another.
In a way, yes. And what's crucial is that smooth perfect complexes behave very well under base change. They retain their smoothness property, which allows us to deduce information about the larger spaces they are associated with.
So we're using this base change technique to propagate smoothness from smaller spaces to larger ones,
Right.
giving us insights into the global structure.
Exactly. And this idea, combined with other sophisticated techniques, is used to prove the main results of the paper, which establish the connection between the properties of perfect complexes and the algebraizability of rigid analytic varieties and formal schemes.
Before we get to those results, can we delve a bit deeper into the concept of perfect complexes themselves?
Sure.
What are some of their key properties, and how do they capture the geometric information we're interested in?
Of course. Perfect complexes reside within derived categories or stable infinity categories, which are mathematical structures that allow us to study sheaves in a more flexible way.
I remember we touched upon sheaves earlier, those labels attached to points that carry algebraic data.
Yeah.
Can you remind us how they connect to perfect complexes?
Certainly. Perfect complexes are essentially complexes of sheaves, meaning sequences of sheaves connected by maps. They have certain desirable properties, particularly concerning how they behave under operations like taking duals or tensor products. These properties make them suitable for capturing the local geometry of the space.
It sounds like we're moving into some pretty abstract territory here.
It does get abstract, but the payoff is that perfect complexes provide a powerful framework for studying geometric properties. One crucial aspect is that they capture information about the derived nature of the space, meaning they take into account not just the sheaves themselves, but also the relationships between them.
So it's not just about the individual data points, but also how those data points are connected and interact with each other.
Precisely.
Yeah.
And this derived perspective is essential for understanding the subtle aspects of geometry, especially when dealing with infinitesimal information, as we do with formal schemes.
This is fascinating. But I must admit, my brain is starting to feel a bit overloaded. Can we maybe step back for a moment and revisit the big picture?
Yeah.
Why are we going to all this trouble to study perfect complexes and their properties? How do they ultimately help us understand algebraization?
That's a great question. Remember that our goal is to determine when these complex geometric objects, rigid analytic varieties, and formal schemes can be represented by simpler algebraic structures.
Right.
Perfect complexes, with their ability to capture local geometric information and their connection to algebraic objects through sheaves, provide the bridge between these two worlds.
So by analyzing these perfect complexes, we're essentially looking for hints of a hidden algebraic structure underlying the geometry.
Exactly. And the properties of these complexes, especially smoothness, serve as indicators of whether such an algebraic structure exists. It's like having a set of diagnostic tools that allow us to probe the geometry and determine if it's amenable to an algebraic description.
I see. It's like we're using these sophisticated mathematical tools to X-ray the geometry and reveal its inner workings.
Yes.
And the paper provides specific criteria based on these tools to determine whether algebraization is possible.
You got it. It's a remarkable achievement in the field of algebraic geometry, and it highlights the power of abstract thinking and the elegance of mathematical reasoning to uncover deep connections between seemingly disparate areas of math.
This is truly mind-blowing. I'm excited to dive into those specific criteria and the main results of the paper.
I'm happy to guide you through them. It's a journey into some of the most fascinating areas of modern mathematics.
Let's continue. All right, let's get to the heart of the matter.
Yeah.
The specific results about algebraization that Montagnani presents in this paper.
Excellent. This is where all our previous discussion about perfect complexes, smoothness, and the distinctions between rigid analytic varieties and formal schemes really comes together.
I'm ready to see how it all plays out. What are some of the key theorems, and what do they tell us?
One of the most striking results is theorem point 2, which focuses on smooth and proper rigid analytic varieties. It states that such a variety is algebraizable if and only if its category of perfect complexes is also smooth and proper.
Okay, that's a powerful statement. It means we have a definitive test for algebraizability in this setting just by analyzing the properties of those perfect complexes.
Exactly. The if and only if aspect is crucial. It tells us that smoothness and properness of the perfect complexes are both necessary and sufficient conditions for algebraization. It's a very tight connection.
So it's like a perfect diagnostic tool. If the perfect complexes exhibit these properties, we know for sure that the variety has a hidden algebraic structure.
Precisely. And this result has significant implications. It essentially allows us to translate geometric questions about rigid analytic varieties into algebraic ones, which can often be easier to tackle using the tools of algebraic geometry.
That's a huge win. It's like having a secret decoder ring for this abstract geometric world.
Indeed. Now, The proof of this theorem is quite intricate, but one of the key ingredients is the concept of simple objects, which are special types of perfect complexes that in a sense represent the building blocks of the category.
Okay, so we're going even deeper, analyzing the structure of those perfect complexes themselves. What makes these simple objects so special?
Simple objects have the remarkable property that their endomorphism algebras are particularly well behaved. In many cases, these algebras are isomorphic to the base field, which considerably simplifies the analysis.
So by focusing on these simple objects, we're essentially looking at the simplest building blocks of the category,
Right.
which makes the problem more manageable.
Exactly. And Montagnani cleverly uses these simple objects to construct an embedding of the rigid analytic variety into a larger space called the moduli space of simple objects.
Moduli spaces. We encountered those earlier. They're geometric spaces that parameterize families of objects, right?
Yes. In this case, the moduli space of simple objects captures all the possible ways those simple perfect complexes can vary.
So it's like a catalog of all the building block variations.
Precisely. And the fact that we can embed the rigid analytic variety into this moduli space tells us something profound. The varieties geometry is, in a sense, controlled by the behavior of those simple objects.
Wow, that's fascinating. It's like those simple objects hold the key to unlocking the algebraic secrets of the variety.
Indeed. And the final step in the proof involves showing that this embedding has some very special properties. It's injective and étal.
Can you remind me what those terms mean again?
An injective map means that distinct points in the original space get mapped to distinct points in the target space, with no collapsing or overlapping allowed. An étal map is a bit more technical, but essentially it means that the map locally looks like an isomorphism. It preserves the infinitesimal structure of the space.
So this special embedding preserves both the distinctness of points and the local geometric structure.
Precisely. And these properties are crucial for establishing the algebraization result. They allow us to transfer the algebraic structure from the moduli space back to the original rigid analytic variety.
This is incredible. It's like a chain of logic, each step building on the previous one, leading to this beautiful conclusion about algebraizability.
I agree. It's a testament to the power of abstract thinking and the elegance of mathematical reasoning. Now, as we discussed earlier, the story for formal schemes is a bit more subtle.
Right. We saw that smoothness of the perfect complexes isn't always enough to guarantee algebraizability in that case. What are the key takeaways for formal schemes?
For formal schemes, Montagnani focuses on two important corollaries, point 3 and point 4, that highlight the nuances of algebraization in this setting. Corollary point 3 states that a smooth and proper formal scheme is algebraizable if and only if its category of perfect complexes is smooth and proper.
Okay, that sounds very similar to the result for rigid analytic varieties. What's the catch?
The catch is that properness is a much stronger condition for formal schemes than it is for rigid analytic varieties. It essentially means that the formal scheme is already close to being algebraic.
So in a way, this corollary is less surprising. It's more like a confirmation that if a formal scheme already looks algebraic, then its perfect complexes will reflect that.
Exactly. Now, corollary point 4 is where things get really interesting. It focuses on a specific category associated with a formal scheme called cobex.
Remind me, what does cobec represent again?
Cobex is the category of bounded coherent sheaves on the formal scheme. Coherent sheaves are a fundamental concept in algebraic geometry, and bounded essentially means that the sheaves have finite support. They are non-zero only on a finite part of the space.
Okay, so we're looking at a specific type of sheaf, the bounded coherent ones. And what does this corollary tell us about them?
Corollary 0.4 states that if cox is smooth, and the rigid generic fiber of the formal scheme is also smooth, then the formal scheme is algebraizable.
Interesting. So the smoothness of this sheaf category, combined with smoothness of the rigid generic fiber, is enough to imply algebraizability.
Precisely. But here's the crucial point. The paper also highlights that in general, we cannot expect cobex to be smooth for a non-algebraizable formal scheme.
So that's where the distinction lies. Smoothness of cobex is a strong indicator of algebraizability, but it's not always present, unlike the case for smooth and proper rigid analytic varieties.
Exactly. This difference highlights a fundamental distinction between these two types of geometric spaces and the challenges of algebraization in the formal scheme setting. It's a reminder that even with powerful tools like perfect complexes, there are still subtle mysteries to unravel in the world of mathematics.
This has been an incredible journey. We've gone deep into the heart of some truly abstract concepts, categories, sheaves, perfect complexes, moduli spaces, simple objects. And it's amazing how they all come together to tell this story of algebraization.
I couldn't agree more. And what's most exciting is that this is just the beginning. Montagnani's work opens up new avenues for research, inviting us to explore further connections between algebra and geometry and to push the boundaries of our understanding of these fascinating mathematical objects.
This deep dive has been a truly enriching experience. It's incredible how much we've uncovered about the relationship between algebra and geometry and how these powerful tools of perfect complexes allow us to explore the hidden structures of these abstract spaces. I feel like I've gained a whole new perspective on the world of mathematics.
I'm delighted to hear that. And remember, the journey of mathematical exploration never truly ends. There are always new questions to ask, new connections to discover, and new depths to explore.
Well said. And to our listeners, thank you for joining us on this deep dive. Keep those minds curious and keep exploring the fascinating world of mathematics. Welcome to another deep dive. Today we're going on a bit of a journey into algebraic and analytic geometry.
Oh, very exciting.
Yeah, I think it'll be fun.
Yeah.
So we're going to be kind of looking at this idea, algebraization, which is like figuring out when you can translate a geometric object that's defined using analytic methods into the language of algebraic geometry.
Yeah, it's a fundamental question that's kind of fascinated mathematicians for decades.
Right.
And the paper that we're looking at today, Algebraization of Rigid Analytic Varieties and Formal Schemes via Perfect Complexes, provides some really groundbreaking insights using some really elegant mathematical machinery.
Yeah, our listeners are very familiar with this area of mathematics. So, feel free to really get into the weeds a bit here. But maybe we can start with just like, what exactly are we dealing with here?
Right.
I see rigid analytic varieties and formal schemes popping up.
Right. These are our main players in the story. So think of a rigid analytic variety as a geometric object that's defined over a field with a non-trivial valuation, like the p-adic numbers.
Okay.
They provide a framework for doing analysis in a non-Archimedean setting.
Interesting.
Formal schemes, on the other hand, are a bit more algebraic in nature.
Okay.
But they play a similar role, providing a bridge between algebraic geometry and analysis.
Okay, so we've got these geometric objects, but they're kind of living in different worlds.
Yeah.
The analytic and the algebraic.
Exactly.
And the big question is, can we find a way to translate between these two worlds?
Precisely. Can we find a corresponding object in the world of algebraic geometry that captures the essence of our analytic object? That's what we mean by algebraizable.
Gotcha. And that's where this idea of perfect complexes comes in, right?
Absolutely.
That's key.
Perfect complexes are kind of like these powerful lenses that allow us to study the deeper structure of our geometric objects.
Okay.
So they capture information about the homota type of a space, which goes beyond just the basic shape.
So it's not just about like finding a corresponding object.
Yeah.
It's about finding a corresponding object that also preserves this deeper structure.
Precisely.
I see. And the paper claims that smoothness is a big deal here.
Right. Smoothness in this context is kind of this desirable property.
Okay.
It means that our space is well behaved. No sharp corners, no weird singularities. But here's the catch. Smoothness in the algebraic world and smoothness in the analytic world don't always line up perfectly.
Oh, so that's where the challenge lies.
Exactly.
Can you walk us through the main theorem of the paper?
Sure.
I know it establishes like a precise connection between algebraizability and the smoothness of perfect complexes.
Of course. The main theorem states that a smooth, proper, rigid analytic variety, or a formal scheme, is algebraizable if and only if its category of perfect complexes is also smooth and proper.
So it's like we have a dictionary.
That's a great analogy.
If our perfect complexes are smooth and proper, we can translate.
We can translate.
But if they're not, then we're out of luck.
Exactly. Smooth and proper perfect complexes provide the translation guide from the analytic world to the algebraic one.
Okay, cool. Now, I know this paper is quite technical.
Okay.
But I think our listener would really appreciate like a peek under the hood.
Okay.
Could you give us just a glimpse into how this theorem is proved?
Certainly.
What are some of the key ideas and techniques that are involved?
So one of the crucial tools the paper employs is this concept of simple objects.
Okay.
Within the category of perfect complexes. Think of these as kind of the fundamental building blocks of our category.
Okay.
They have a very specific property. their endomorphism algebra after a suitable base change
Yeah.
is as small as possible.
Small in what sense?
So in more technical terms, we're looking for objects whose endomorphism algebra is concentrated in degree 0 and is just a copy of the base ring. These simple objects capture the most basic, irreducible pieces of information about our geometric object.
So it's like we're breaking down this complex into its most fundamental atoms. But how do these simple objects help us actually prove the algebraizability theorem?
The paper establishes this.
We're matching up the entire structure of how these objects are related to each other.
Exactly. And once we have this bridge, we can start transferring properties back and forth.
I see.
The paper then shows that our original rigid analytic variety can be embedded into the coarse moduli space of this stack of simple objects. This embedding is a crucial step towards proving algebraizability.
Okay, we're starting to see the outline of the proof emerge here.
Yeah.
But I have a feeling there's still some missing pieces.
What else do we need to establish algebraizability? You mentioned coarse moduli space.
Right.
Can you unpack that term for us a little bit?
Of course. So you see stacks, while they're powerful, can be a bit unwieldy.
Okay.
They carry a lot of extra baggage in terms of information about symmetries and automorphisms.
Right.
The coarse moduli space is kind of a way of forgetting some of that extra structure and getting a more manageable space that still captures the essence of the original stack.
So it's like we're taking like a simplified snapshot
of the stack.
Yeah.
But why is it important to embed our rigid analytic variety into this coarse moduli space?
That's where this really cool concept called non-Archimedean Moishazon spaces comes into play.
Moishazon spaces.
Yes.
I've heard whispers of their magical properties.
They have kind of a technical definition, but essentially they're a special class of rigid analytic varieties that are close to being algebraic.
Interesting.
And the crucial result is that if we can embed a rigid analytic variety into the analytification of a proper algebraic space in a nice way, then that variety must itself be algebraizable.
So it's like Moishazon spaces give us like a litmus test for algebraicity.
Exactly.
If our rigid analytic variety can kind of be embedded into this Moishazon space in the right way, then we know it has like a secret algebraic identity.
Precisely. And in our case, the paper demonstrates that the embedding that we constructed earlier, the one into the coarse moduli space, passes this test. It satisfies the specific properties required to invoke the Moishazon criterion.
Okay, so we've connected a lot of dots here.
We have.
Simple objects, stacks, coarse moduli spaces, and now these Moishazon spaces.
Yeah, it's quite a journey.
It's an intricate web of mathematical concepts.
It is.
But I want to make sure that we're not getting lost in the abstract here.
Great.
Can you give us a concrete example of how this all works in practice?
Sure. Let's consider the case of elliptic curves.
Okay.
So you're probably familiar with these from your studies.
Yeah.
They're smooth projective curves of genus 1.
Right.
Over the complex numbers, an elliptic curve can be described analytically as a complex torus, which is just a complex plane modulo, a lattice.
Right. Remember those beautiful pictures of lattices and torus.
Yeah.
But how do we translate that analytic picture into, like, algebraic language?
That's where our machinery comes in.
Okay.
We can consider the category of perfect complexes on this complex torus.
Okay.
And it turns out that this category is smooth and proper.
Moreover, we can inevitably identify the simple objects in this category. And they correspond to certain line bundles on the torus.
Line bundles.
Right.
Can you remind us what those are?
So think of a line bundle as a way of assigning a line. Or a one-dimensional vector space to each point on our space. In the case of a torus, these line bundles are classified by their degree and a complex parameter.
So we have these simple objects, line bundles, on our torus.
Right.
How do we use them to prove algebraizability?
So we can construct the moduli stack of these simple objects, which turns out to be an algebraic stack. Then we can take the analytification of this stack, which gives us a rigid analytic stack. And the beauty of this construction is that our original complex torus embeds into this analytified moduli stack in a very nice way, satisfying the conditions of the Moishazon criterion.
So we've embedded our analytic elliptic curve into a space that we know has an algebraic counterpart.
And the Moishazon criterion tells us that this implies that our elliptic curve must also have an algebraic description.
Precisely.
Wow.
In this case, the algebraic description is given by a Weierstrass equation,
Okay.
which is a cubic equation in two variables.
Right.
This equation defines an algebraic curve that is isomorphic to our original complex torus.
That's amazing.
It is.
We started with an analytic description of an elliptic curve.
Yeah.
And using this very intricate machinery,
Right.
we've recovered its algebraic representation.
We have.
It's like a beautiful example of how these different branches of mathematics,
All right.
analysis, and algebra are really just intertwined.
They are. It highlights the power of this approach.
Yeah.
We can use tools of homological algebra and category theory to bridge the gap between these analytic and algebraic worlds.
Yeah.
And the results aren't just abstract theorems.
Right.
They have concrete applications in understanding specific geometric objects.
Yeah, this has been incredibly illuminating.
It's a fascinating topic.
Right. But I know we haven't even touched on the formal scheme side of the story yet.
Right, the other half.
I'm eager to hear how these ideas extend to that setting.
Okay.
But perhaps we should take a short pause here and let our listener kind of digest everything we've covered so far.
Sounds good.
Okay. So let's dive into this world of formal schemes. I have a feeling things might get even more intricate here.
You're right. Formal schemes present some unique challenges and insights.
Yeah.
But the framework that we've already kind of developed for rigid analytic varieties provides a really solid foundation for tackling this new terrain.
I remember you mentioning something called rigidification earlier.
Yay.
Can you remind us how that concept helps us bridge the gap between these formal schemes and rigid analytic varieties?
Absolutely. So rigidification is essentially a way of associating a rigid analytic space to a formal scheme.
Okay.
So it's like analytifying our formal scheme,
Right.
allowing us to view it through this analytic lens.
So we're taking our formal scheme, which is defined algebraically, and we're kind of constructing this corresponding analytic object that captures its essential features.
Exactly.
And then the key insight is that the category of perfect complexes on our formal scheme is somehow connected
very connected
to the category of perfect complexes on its rigidification.
Right. In fact, the paper establishes an equivalence between these two categories after a suitable base change.
So we're back in familiar territory.
Yes.
We're connecting the world of formal schemes to the world of rigid analytic varieties.
Exactly.
Through this language of perfect complexes.
Through these perfect complexes.
But how does this equivalence actually help us with like the algebraization problem?
So the strategy is pretty elegant.
Okay.
If we can show that the rigidification of our formal scheme is algebraizable, then we can actually use this equivalence of categories to deduce that the formal scheme itself must also be algebraizable.
So it's like we're using the rigidification as a stepping stone. We prove algebraizability in this analytic world, and then we can kind of lift that property back to the algebraic world.
Lift it back up.
Of formal schemes.
Precisely.
But I feel like we encounter a familiar obstacle. This whole mismatch.
That's right.
Between analytic smoothness and algebraic smoothness.
Yeah.
I feel like that issue would also complicate things.
It does.
In the formal scheme setting. How does the paper address that?
So the paper actually provides two different criteria for algebraizability in the context of formal schemes.
Two criteria.
Two different paths leading to the same destination.
Okay. I'm intrigued. Can you elaborate a bit on these two different approaches?
Certainly. So the first criterion states that if the category of perfect complexes on our formal scheme is smooth and proper, and its rigidification is also smooth, then the formal scheme is guaranteed to be algebraizable.
So we need both the formal scheme itself and its rigidified counterpart to exhibit these nice smoothness properties.
It's a double smoothness check.
Yeah, a double check.
And the proof of this criterion leans heavily on the results that we've already kind of established for rigid analytic varieties.
Right.
So essentially we're showing that the algebraizability of the rigidification implies the algebraizability of the original formal scheme.
So we're building on our earlier work.
Exactly.
And establishing this chain of implications.
Right.
That ultimately leads to algebraizability in the formal scheme setting.
Precisely. But the second criterion offers a slightly more fascinating perspective. It asserts that if the category of coherent sheaves on our formal scheme is smooth, and its rigidification is smooth, then the formal scheme must be algebraizable.
Wait a minute, coherent sheaves?
Yes.
Didn't you mention earlier that like the smoothness of coherent sheaves
I did.
isn't always guaranteed in this realm of formal schemes?
That's right. And that's what makes the second criterion so remarkable.
Oh, okay.
It highlights this very subtle but crucial distinction between the world of schemes and the world of formal schemes. So in the world of schemes, the smoothness of coherent sheaves is kind of a natural consequence of the smoothness of the scheme itself.
Right?
But in this more general setting of formal schemes, that implication doesn't always hold.
So in a sense, this second criterion is kind of like a test for whether our formal scheme is behaving like a scheme
Exactly.
in terms of its coherent sheaves.
Precisely.
If the coherent sheaves are smooth, it's suggesting that our formal scheme might be close enough
Right.
to a scheme for these algebraic properties to hold.
That's a brilliant insight.
Oh, thanks.
The smoothness of coherent sheaves in this context acts as this indicator that our formal scheme might be amenable to algebraization.
Wow, this is mind-blowing.
It is.
We have these two very powerful criteria for algebraizability,
Right.
both rooted in our understanding of rigid analytic varieties
Yes.
and highlighting these very subtle distinctions between different geometric settings.
Exactly.
But the paper doesn't stop there, does it?
No, it doesn't.
It seems like it goes even further to explore like the boundaries of these criteria.
You're absolutely right. The paper goes on to investigate situations where these criteria actually fail.
Okay.
And it provides concrete examples that demonstrate the necessity of these assumptions that we've made.
So it's not just about proving theorems, it's about understanding their limitations
Exactly.
and the nuances of these geometric worlds.
Precisely. And that's what makes this area of research so captivating.
Yeah.
It's this constant exploration, a journey of discovery,
Right.
and an invitation to delve deeper into these mysteries of the mathematical universe.
This deep dive has been an incredible adventure, a thrilling climb through the peaks and valleys of algebraic and analytic geometry.
It has.
We've explored these profound concepts, uncovered surprising connections,
Absolutely.
and kind of glimpsed this intricate machinery that mathematicians use to unravel the secrets of the mathematical world.
It's been a true pleasure to share this journey with you and our listener. And I hope that this deep dive has sparked a sense of wonder and a desire to continue exploring these infinite depths of mathematics.
I have no doubt it has.
Yeah.
And on that note, we bid farewell to our listener, leaving them with the echoes of these profound ideas and the inspiration to embark on their own mathematical adventures. Until next time, may your explorations be filled with curiosity, insight, and the joy of discovery.